And good afternoon, everyone. Welcome to this second installment of the mini school on the simulation of quantum systems, closed and open. And again, we have Ian Joel David as a speaker. Ian is a PhD student at UKZN and is also affiliated with NITheCS as a bursary holder. So, Ian, you already gave us a very nice introductory lecture last week that unfortunately I missed, but I watched it later on YouTube. You're most welcome to start with lecture number 2. Thank you very much. And the usual rules of the game apply. Yeah, please make use of the Q&A to ask questions. And at the end of the talk, we can also give you the opportunity to ask questions in person. Thank you very much, Ian. Over to you.
Thank you, Prof. Okay, good afternoon to everyone who's here. Yeah, so as Prof mentioned, we're back to learning about the quantum simulation of closed and open quantum systems. And now we're at lecture 2. So last week I mentioned as a brief, sort of preview that we're going to be talking about Trotter-Suzuki product formulas. So last week we very nicely formally stated the problem of quantum simulation. And today's lecture, we're going to see how we can use the method of Trotter-Suzuki product formulas. So I should mention this is just one method of solving the problem of quantum simulation, but we're going to look at how we can use Trotter-Suzuki product formulas to solve the quantum simulation problem. Okay. All right. So let's recap the problem of quantum simulation. Okay. So we know that when we're dealing with closed quantum systems, the object of interest is going to be the Hamiltonian. Okay. So last week, where we left off is we said that we're given a Hamiltonian H, which is a sum of smaller terms Hj, and by smaller, I'm referring to something called simpler, which I'll explain in a moment. A simulation time t that's bigger than 0, some precision epsilon, and an initial state of our quantum system, which is the ket psi 0. The idea here is to construct some approximation u tilde of t to the time evolution operator u of t, such that the norm of the difference between them is bounded by the precision epsilon. So it means that u tilde of t approximates u of t. Okay, and the other caveat is that the approximation, as we said, it should be efficiently implemented on a quantum computer using a polynomial number of quantum gates. So this is where we left off last week, and this is just the most general way we can write the problem of simulating a closed quantum system. So as you can see, there's many components to this problem. The first one is going to be finding the Hamiltonian in a form like this. And the second one, which is of most vital importance, is how do we build this approximation u tilde of t? So there's many different ways you can approximate the time evolution operator, but we need to remember build this u tilde of t in such a way that we can efficiently implement this on a quantum computer. Because a very straightforward way one can tell me to do it will be just write down e to the minus I ht as a Taylor series, truncate at some order, and then you're done. But how to implement that on a quantum computer efficiently is also a bit tricky. And we may even talk about that in a later lecture. But I want to construct this u tilde of t in a very simple way, such that I can implement it efficiently on a quantum computer. And the answer to how we can start doing this is if we construct u tilde of t as a product of simpler unitary operators. This is a nice starting point. We have already, it's popping up on the screen. Okay, so the idea then would be to come up with some product of unitary operators, say Vj of t, such that they will approximate our time evolution operator. Now, why is it that we want a product of unitary operators? So if you've done any quantum computing, you'll know that, well, even some quantum mechanics, you'll know that the product of two unitary matrices is again a unitary matrix. And in quantum computing, when we apply gates to our register of qubits, they're all unitary operators, and products of them are again unitary. So we very nicely want a product of unitary operators as an approximation. And we'll see later why it's even more important that we need this product of unitary operators. But the motivation for why we want this is because we will want an approximation that we can implement efficiently on a quantum computer. And another important point that we should note is that we want to find this product in such a way that when we go to estimate the error bounds and the number of repetitions that we need, or the number of unitaries that we need here, we want this to be, fairly easy to do without specific knowledge of what the Hamiltonian of the system is. So we need a nice way to construct this U tilde of t in such a way that without we're just saying that the Hamiltonian is a Hermitian operator, we should be able to come up with an error bound and a bound on the number of unitaries that we need in this product. Okay? And this is where the first order Trotter-Suzuki product formulas come in. Okay? So for the moment, for the time being, let's simplify everything that we're doing by just taking a Hamiltonian that is just H1 plus H2. This is going to make our analysis a lot easier, and the motivation and the analysis of this, what we're going to call the first order Trotter-Suzuki product formula, very, very straightforward. Okay? So if this is what our Hamiltonian is, then we need to construct an approximation to the time evolution operator, which is e to the minus I H1 plus H2 on t as a product of other unitaries. Okay, so the natural thing, and the natural starting point is to use the unitaries e to the minus I H1 of t and e to the minus I H2 of t. So these are on their own are individual unitaries. And if we can write down an approximation that is a product of these two things, and we can show that it approximates the time evolution operator, then we have our approximation that will solve the quantum simulation problem. And this is a very natural thing to do because it comes from what we call exponential splitting. So you may recall from course in math methods or maybe advanced course in quantum mechanics or something like that, where you studied the exponential of a sum of operators. And your lecturer may have told you that it's not as straightforward as doing the exponential of a sum of numbers, because if you have the exponential of a sum of numbers, it's easy, you just use your exponential rules. Well, when they're a sum of operators, it's no longer so straightforward. And something you may recall would have been something like the Baker-Campbell Hausdorff formula, which allowed you to split up this exponential of a sum of operators. Okay? So we know that this idea of exponential splitting is pretty complicated, but we can use it to our advantage to say, okay, we want to construct this U tilde of t as some product of these two individual unitaries. Okay? So to do this, we start by recalling an exact splitting, an exact way to write this as a product of these two, which is called the Trotter formula, okay? Or the Lie-Trotter formula. If you literature, most of the time you see this as Trotter formula. And the Trotter formula tells us that we can split up an exponential like this here by very simply taking the limit as n goes to infinity, writing them as a product of this two, dividing t by n on both sides, and then taking it all to the power n. So this is a very nice way to exactly split up this exponential that you have here, okay? However, we can't use this to solve the quantum simulation problem because, to say that, this is exactly equal to the limit as n tends to infinity is not practical enough for us. What we really need is we need something that we can use to then do an approximation of the time evolution operator, and we can get things like specific precision, and also we want to find a bound on this n. Okay. So as I said, what we really want to do is say that this time evolution operator is approximated by the product or the Trotter formula for large enough n. Okay. So whereas we just drop the limit and we now say that it's approximately equal to this, but we need to figure out what this n is going to be for us to be able to do any type of rigorous analysis using this this approximation of the time evolution operator. So what we're going to do now is we're going to start with a formula like this, and we're going to show how it approximates the time evolution operator. So we're going to use this as what we would call u tilde of t, and we're going to give this a name. This is called the first order Trotter-Suzuki product formula. Okay. So let's start our analysis by trying to show that that we have this approximation. So let's start by defining tau as being t over n. Okay, this is going to make our analysis a bit easier, so we don't have to keep writing t over n all over the place. And then, of course, we observe the following thing, that if we start with the time evolution operator u of t, that we can write e to the minus iht as e to the minus iht over n, all raised to power n. And on the inside here, we'll just put e to the minus ih tau, and this is just u of tau to the power n. Okay? And the next thing we'll write, which we'll call our first order Trotter-Suzuki product formula, is just going to be the product of e to the minus ih1 on tau times e to the minus ih2 on tau. This is our Trotter-Suzuki formula, and it's going to be our approximation. So what do we need to show now? If we want to use this to approximate the time evolution operator, we need to show that the difference between this and this, their norm is going to be bounded by some precision epsilon. And I should have here tilde. Okay? So this is what we need to show. We need to show that when we take the norm of the difference of these operators, then it's going to be bounded by some precision epsilon. And for the most part, when you're developing quantum simulation algorithms, this problem makes up a large chunk of what you need to do when you're doing this. You have the approximation, and this is not a straightforward thing to do. And the reason why we start with the Trotter-Suzuki formulas is because the analysis is a lot simpler than some other algorithms that already exist. So this is going to make up at least half of the lecture. We're going to go through how to do this type of bound. Okay, and I'm going to walk you through the steps, and the idea will be for you to then go home as homework or an exercise, generalize this to the case when the Hamiltonian is a sum of from h1 to hm. But we're just going to start by doing the analysis for this very, very simple formula, and I'm going to show you some interesting techniques that we use when we're doing Hamiltonian simulation into finding this bound. But once we find a lower bound on the precision epsilon and this number n, because remember n, you can't just say, okay, if n is large enough, then it's approximately equal. If we're going to do some sort of practical simulation, we need a lower bound on what n should be, or some sort of explicit natural number value for n, which you can calculate with something like a ceiling function, so that we can actually do some type of quantum simulation. So when we're doing this type of analysis, it's never enough to say for large enough, or this approximates this to epsilon. We need explicit bounds, because that's how we can implement these algorithms on the quantum. So this is our starting point. Let's now start to show this inequality, because this is going to make up a large chunk of what you do in quantum simulation, is proving inequalities such as this. Okay. Are there any questions at this point that anyone has in the audience on Zoom? There's nothing, then I'll move on. Okay. Everyone's fine. Okay. So let's start in trying to prove this identity. Okay. We will use the following identity or relation, which you can find in any reference material or even some papers, which detail this inequality here, which is usually proven by induction, is that for any operators a and b and some natural number p, the difference inside this norm is bounded by p times the difference of the norm of the difference of the operators. So this is going to be very, very useful when we are proving these types of inequalities. And the reason for this is because, if you recall from the previous slide, I was able to write u of t as u of tau all to the power n. Okay, so if we start out with the inequality which you want to show, we say that this is equivalent to u of tau to the power n minus the approximation, or our first order Trotter-Suzuki product formula. Using the identity above, we can write it as n times the difference between the u and u tilde. Okay, and therefore, if we want to complete the proof, we need to bound this quantity with a small times. So to do this, we need to start by making a Taylor expansion on u of tau, okay, because tau is a small time step. So I've shown you already in the first lecture how you can write down the function of an operator as a Taylor series. So, and I mentioned that the exponential formula is going to be very, very important. And this is where you see it, right? So we write down the Taylor series for e to the minus I h tau. And what we see here is that we can write this as the sum here with this factor in the front on h1 plus h2 all raised to the power k. This is just a standard Taylor expansion of u of tau. Okay, so the next thing we need to do when we're doing this is we want to also Taylor expand the approximation u tilde of tau. Because what we're going to do is when we do these Taylor expansions is we're going to compare terms and check the terms that cancel. Okay, so how do we go about Taylor expanding this approximation? Well, we need to Taylor expand the individual exponentials. So you're going to have two Taylor series. That's why I have two sums here that go from over the indices k and l. And then this is what the Taylor expansion looks like. Okay. Now, what you would need to show that I skip in the slide, but it's fairly easy to do, is you need to write out the terms of these Taylor expansions explicitly and check which orders cancel. Okay. There's a lot more complicated tools that they use to determine to what order an approximation approximates the time evolution operator, and these are called order conditions. But because we're doing just a first order expansion, we don't need these more fancy tools to do that or fancy theorems to do that. All we can do is we just explicitly write out the zeroth order term and the first order term, and you'll see that they cancel explicitly. Okay. And from this, you can very easily see that the zeroth order term is going to be identity on both sides. And the first order term here will just be minus I tau on H1 plus minus I tau on H2. Because at the first order term, you're obviously going to get one being L being 0 and then K being 0. So you'll just have a first order term. And by first order, what do I mean? I mean, is that we'll just look at the power of tau. So when I talk about second order term, I'm referring to tau squared, and the third order term will be tau cubed, so on and so forth. But in general, what you would need to do is, as I said, you would need to write down explicitly the terms and then check if they cancel. So we see that for this approximation, it cancels up to first order with u tau, u of tau, the time evolution operator, exactly, leaving only second order terms that remain. So that's why when I take the difference of this expansion and the previous expansion, we see here that the first order terms are gone because I start k from 2. Because they cancel, I don't care about them. So I just write down from k is going from 2 to infinity in that Taylor expansion of the time evolution operator. Similarly, the 0th and the first order terms from this expansion, they're also not going to be present because they canceled with the 0th and first order terms from here. So that's why I start the sums from k and l going from 2 to infinity. And this now is going to be the quantity that we're going to try to bound, and it's going to be the lower bound on our precision. Okay? So already it may look a little bit daunting, it looks a bit challenging, but using the properties that we learned about last week, such as sub-additivity and sub-multiplicativity, as well as the triangle inequality, we'll see that this very quickly becomes a very, very straightforward problem. And it doesn't become complicated at all. Okay? So are we all clear on how I got to this step and why the terms cancel? Okay, because if you don't understand, cancel just means that the identity minus identity on this side, tau h1 minus tau h1 on this side, and that's what I mean by cancel. Okay, so let's move on from here. Okay, so because you want to bound the precision, you need to take the norm of both sides. And now you're left with this extremely big expression, which you need to do some simplification on. So the first thing we would do is we apply the triangle inequality. Because if we apply the triangle inequality, we can say that this difference is bounded by the norm of this term plus the norm of this term, which is what you see here. Okay? And all the triangle inequality is if you have the norm of A plus B, it's less than or equal to the norm of A plus the norm of B. Okay, so all I did was I just applied the triangle inequality to the first term here, and the minus sign goes away because when you take the norm of something that's negative, you pull out the minus sign absolute value, so you get just plus 1. So that's why there's no minus sign here. Okay, so far we've not done anything complicated, we've just applied the triangle inequality. It looks complicated because there's a lot of sums and a lot of indices and a lot of operators, but it's not bad. It's not crazy at all. So let's go individually and look at the terms. Okay. So if I look at the first term that's present here, this is the norm that we need to bound. We can apply the triangle inequality repeatedly so that we can take the norm inside of the sum. So the norm goes inside the sum. When the norm goes inside the sum, all the scalar quantities can be pulled out to the front, and we just take the absolute value. So that's what you see here. All the scalar quantities have been pulled out, and we put it in the absolute value because, of course, this is a minus I inside there, so we can't just take it out exactly. And the norm is only focused on the operator H. Okay. We can also then use what we call the submultiplicative property. So if you have a product of operators, and I think I wrote it down in last week's slide, but I'll write it at the top here as well, is that if you have the norm of A times B, okay, then this is less than or equal to the norm of A times the norm of B. Okay, that's effectively the property that we've used here, and they just generalize it so that when you have A to the power K, the norm of that is just going to be the norm of A to the power K. So that's all we've done here is we've replaced this H, the norm of H to the power K by the norm of H to the power K. And we have the inequality symbol that we see here. Okay, so this is the quantity that we need to find bound for. Okay, and to do this, what we need is we need to effectively bound the norm of the Hamiltonian. Now, if I give you an explicit matrix, you should be able to find the norm of this matrix. If I give you an operator, a bit more tricky, but you can, for certain types of operators, very easily find the norm of an operator. However, I've just told you that H is an emission operator. So I haven't really told you much about what H is, its structure, or what form it has. I've only told you that it's a Hermitian operator. And now you need a way to bound this quantity here. And you'd be surprised to hear that you can actually do this without knowing anything about H. And that's what we do most of the time in quantum simulation, is we construct a bound for H, the norm of H, without even knowing what H is. And the way we do that is, if we look at the bottom of the slide, we define a quantity lambda, which is just the maximum of the set here, which is the norm of H1 and the norm of H2. So H comprises of two terms, H1 plus H2. I evaluate the norm of the individual terms, and I take the larger one. Okay. Once I take the larger one, I arrive at the following result. Let's say that the norm of H, after I apply the triangle inequality, is just the norm of H1 plus the norm of H2. Now, lambda is the maximum of these two. So I can just bound this whole sum above as 2 times the maximum. This is a standard thing that you do. If you have the sum of two numbers, you can always say it's that sum is smaller than or equal to the number of terms in your sum multiplied by the largest number in your series. Right? It's just a standard thing you do in real analysis or something like that. We're using the same idea here, which is that we found a way to bound the norm of the Hamiltonian in terms of the maximum of the norms of the individual terms and the number of terms in our Hamiltonian. We'll see next week that while this bound is a very nice trick to finding a bound on the norm of the Hamiltonian, it adds a factor of dependence on the number of terms in the Hamiltonian, which you sometimes do not want, depending on the system that you're studying. Because this means that the complexity of your simulation algorithm is now going to be dependent on the size of your system, which for very large systems is not efficient. But for now, this is fine as a bound that we're going to use, okay? And once we plug this bound into the expression above, we arrive at this following bound for the first term, okay? And this is nothing too complicated. It's straightforward, and what we have here now is we have only scalar numbers in the sum. There's no longer any operators, there's no, and this is what we expect because the norm, as we've said, is a number. So if you want to bound the norm, it should be bounded above by some number, not by operators. So we're happy. Now that we're here, we have this is a somewhat straightforward sum to work with, okay? This leaves only the second term that we didn't study. So let's go in and try to bound the second term, okay? And with the second term, what we see is that if we take the norm of the side, we need to once again go and do triangle inequality and submultiplicativity over and over again, such that we can bound this above in the following way. We've pulled out all the scalars to the front like we've done before. Still have two sums. And here we have the norm of h1 to the power k and the norm of h2 to the power l. Okay, I've used just the same logic again, and you just keep doing it. So the idea is you want to move. Always remember this is very important when you're doing these type of bounds. The idea is to apply your properties of your norm in such a way that the norm keeps moving into the sum, such that all you're left with is the norm of a single operator to some power or something like that. Because we can always bound the norm of a single operator. It's easy to do. So that's what we did here. We kept moving the norm in until we reached a certain stage like this. Okay? Okay. Now we observe the following thing. That we have the norm of h1, and we need to bound it, and we have the norm of h2, and we need to bound it. Well, we can use lambda, which you already defined, and we say that the norm of h1 and the norm of h2 are both bounded above by lambda. This makes it very easy because we're already using lambda in the previous bound, so we want to make use of the similar symbol here. You don't want to have some other bound here. It makes it hard to then combine the sums as we proceed. So we bounded it in terms of lambda. Okay. So what do we have? We say that this bound, or the bound on the second term, is just going to be precisely this quantity here. We have replaced the norms of these operators by just lambda. Now we arrive at a bit more of a tricky step. And it's not so tricky once you know the trick. But it's the idea of trying to compute the sum. The sum looks very, very complicated. It's, you can't replace it by a Taylor series because you have k going from 2 to infinity and not 0 to infinity. So the idea is, how do you find a way to, write the sum in a nice, neat way that you can further the analysis? And the idea is to use this trick of computing restricted sums. So here we see we have two infinite series, right? Now, working with infinite series is always tricky because you need to check things like convergence and stuff like that. However, I can always write these two infinite series as one infinite series and two finite sums. And the way I do that is by adding a restriction. And that's why I call it a restricted sum. And I can always write this as a sum from p going from 2 to infinity, where I sum over k and l from 0 to p, and I have imposed a condition that k plus l must always sum to p. Using this, I can now find a way to compute the sum, or at least the bound on that sum. Okay? And the way we can compute a sum like this, or a restricted sum like this, because this is a finite sum. So there should be a way to compute this finite sum exactly. Okay? I'm not talking about the p going from 2 to infinity, but I'm talking particularly about the finite, there's two finite sums there. There should be a way to compute that finite sum exactly. And the way we go about doing it is by looking at the exponential function. So consider the exponential function for some scalar x, right? Some real number x. E to the 2x is equal to e to the x times e to the x. Remember, x is a scalar. You can only do this here. With an operator, you can't do this. And let's expand both sides in a Taylor series. Okay, we all know how to expand e to the 2x in a Taylor series. It's just going to be the sum from p going from 0 to infinity, 2x to the p all over p factorial. Okay, then let's expand this side of the Taylor series by expanding the individual exponentials. You'll get two Taylor series, okay, where it's x is equal to x to the power q plus s all over q factorial on s factorial. And let's apply the same idea of the restricted sum to this expression. And what do we get? Well, we go with the sum from p is going from 0 to infinity, the sum from q and s going from 0 to p, with the restriction that q and s should always sum to p. Now, we can make some comparison. Because what can we see from here? We can see that we have in the front of this side and in the front of this side, both sums from p going from 0 to infinity. So we can look at the individual terms. So which means the summand inside here and this must be equivalent. Okay? And that's precisely what we come to find out, is that we immediately get this following identity, which is a restricted sum like this is just equal to 2x on p all over p factorial. Okay? Nothing complicated. Are we clear on how I got to that step? Is it clear? Okay. And then if we use this result, with x as being the absolute value of minus I tau times lambda, we get the following bound for the second term in the difference of our first order Chordy-Suzuki product formula and the time evolution operator for a small time step tau. Okay? Now, the reason why we went through all this hassle is because if we now go back to the original bound we're trying to show, we now have two identical sums as a bound for the first term and a bound for the second term. And what does that mean? It means that we can just combine this into one sum with just 2 times the sum. So now we have a very nice, neat bound for the difference between our approximation and the time evolution operator, which is precisely right here. So we're all clear how I got to this step. I just plugged in the individual bounds. So I took the two bounds that we found for the two terms, the two error terms from this approximation, and I just wrote down the bounds and I replaced it by 2 times one of these sums because they're both identical. Okay? And then we need another bound to complete this proof, because here we still have an infinite series of terms. But we want it to be nice as just a single number that we can make some sort of analysis and use it to compute things like the number n or the bound of the number n and the precision. Okay? So I'm not going to show you how to do this, it's a bit more complicated. But you can find this, just on any Wikipedia page. It's just an identity for the bound of the exponential function. So because the exponential function is so commonly used in things like physics and quantum simulation, quantum computing, people have studied it in functional analysis very, very, very well. And they have a whole bunch of different, bounds that you can find in some cheat sheet on the internet. And this is a very important bound that we're going to be using to bound this norm here. And the bound is very, very simple. It's that if you have a sum going from p equals k to infinity of the absolute value of lambda, lambda is just some complex number or scalar. This is bounded above by the absolute value of lambda to the power k, where k is the largest, or is just the term that the index p starts from, the number that the index p starts from, and it's multiplied by e to the power of absolute value of lambda. Now, this looks a bit like complicated, but it's not too bad, because what it's intuitively telling us is that if you look at this quantity here, this is an infinite series from 2 going all the way to infinity. And you have tau as being a smaller and smaller parameter. Okay? So you have tau as being a small parameter. So if you look at tau squared, okay, if tau is something like 1 over 10, then what is tau squared? It's 1 over 100. And then tau cubed is 1 over 1000, and so on and so forth. So what does that mean? It means that the terms, as this goes to infinity, gets smaller and smaller and smaller and smaller with respect to tau. And the dominant term in this whole expression is going to be just the tau squared term. That's going to be the largest contributing term. But we can't ignore the contributions from the other infinite terms. So we need a formal bound to represent the fact that the most dominating term in the series is tau squared, but it's multiplied by some factor which accounts for the rest of the terms that are in the infinite series. And that's formally what this bound is telling us. It's telling us that if you have an infinite series that starts from p is equal to k to infinity, then this whole thing is going to be bounded above by the term that's to the power k, because that's going to be the largest contributing term. Okay? And to account for the rest of the terms in the series, you will have just an exponential factor that's there. Okay? That's just the intuition behind why you need this bound. Okay. So using the inequality above, it allows us to arrive at the following bound, is that the difference between the time evolution operator and the approximation here, which you see you have told of tau, is less than or equal to 2 tau times lambda all squared multiplied by e to the 2 tau and lambda, it's exponential factor. And if we replace tau by t over n, we get our final desired bound, which is just shown here. I'm not going to read it out because too many things. But remember I said we need to bound this above by some precision. So all we do is we use this as the lower bound for our precision, and we choose epsilon such that it's bigger than or equal to this quantity here. And then this is straight, it's already bounded. We don't need to do anything more, and we have that this is bounded. So we've completed our proof. We've bounded the difference in the time evolution operator and approximation by some precision epsilon. Okay? And this, what I've just done, is most of what we do in quantum simulation. Is you come up with very nice ways to approximate your time evolution operator, and you make sure that it is bounded, or this approximation does actually work the way you hypothesize that it does. And once you prove this, you have a precision that you can work with. And from this precision, you can now obtain other bounds. So the next most important thing that you're going to need is going to be a bound on this number n. Because so far, n is not something that you want to just specify. You want to specify the precision, and you should get n. Because it doesn't make sense, because what we're saying here is that the precision is bigger than or equal to this quantity, but you don't want to specify n to find the precision. You want to be able to specify the precision and find n. Okay? And now, with the rigorous bounds on the accuracy of this approximation, I just want to mention how we usually write it before I move on. It's usually we'll say that u of tau is equal to u tilde of tau plus big O tau squared. And all this means is that we have a first order approximation with the error term being quadratic. That's all it means. So usually when you see some type of product formula or some type of approximation of the unitary operator, it will be written in this way here to inform you to what order you're going to approximate the time evolution operator. So in our case, it's to big O tau squared. Okay? So, as I mentioned, we usually want to specify the precision and then find the number of times n we need to apply u tilde of tau. Okay? And to do this, what we want to do is we can either solve numerically this expression for n. Okay, that's one way to go about doing it, is say, okay, you have the precision as being equal to the bound that we have, and you just solve numerically for n. That's one way you can go about doing it. But it makes analysis a bit hard, because then you've got to know all these parameters for you to be able to solve numerically for n. But what happens if we don't want to do that? We just want some sort of formula that we can use in general to state an algorithm. Well, if we choose an n such that this n is large enough that this exponential is approximately 1, then what we can do is that we can easily just choose this n as being the ceiling function, and the ceiling function is just the largest integer, or the smallest integer that is greater than the number that is inside here. If we choose an n that's equal to that, then this exponential is effectively governed by something like e to the the precision e to the power epsilon which is your precision, and if epsilon is small enough, then that's approximately 1. So this is usually how we'll find n. So in most quantum simulation algorithms, what you're going to do is you're going to specify the precision epsilon, you're going to compute this quantity lambda, you'll specify a time t, and you use it to calculate the number of times you repeat your approximation n. Okay? So far we've only talked about the Hamiltonian being the sum of two terms, just so that we can do some analysis in a very straightforward way. But in general, you'd want to show or do the same analysis for a Hamiltonian that is a sum of terms from 1, say, to L. Okay? And using the same method that we did above, we construct the approximation as just a product of e to the minus I hj on tau. And going through the exact same steps that we did before, the only difference being you'll have a lot more h1 to h2 times h3 times h4, so on to deal with, but it's precisely the exact same thing. Even the step of the restricted sum is exactly the same. Instead of doing e to the 2x, you'll do e to the lx, and you repeat the same argument. All you do is wherever we had 2, you're going to replace it with L, because 2 was accounting for the number of terms that we had. Okay, so the next thing that we want to talk about is what is the bound with respect to this first order Shorter-Suzuki product formula and the time evolution operator. Well, I'm not going to show it, but you can show it for yourself. The difference is just going to be bounded above by this quantity here, which is less than the precision, and we can use this to determine n, which is given by the ceiling function here. Equals to sign in here. Okay. And lambda in this case is no longer just the maximum value of the norm of the individual Hamiltonian hj. It's going to be the maximum of the norm of all the summands in H. So in that case, it's just the largest, the norm of the largest norm of this hj's in the sum is going to be your lambda. So whereas previously it was the largest norm between the norm of h1 and h2, now it will be the largest over all the norms of all the smaller terms in H. Okay. And then the natural question that one asks is, okay, we've only ever looked now at a first order approximation, but what happens if I want to increase the accuracy of my approximation? Then I need to go to higher orders. Okay. And this was done by Suzuki. Okay, so Suzuki addressed this problem of using these product formulas to go to higher orders. Okay. So far I've used U tilde of tau, but formally in the literature, we don't usually write down U tilde of tau. What we prefer to write is this notation here where we use S and a subscript to denote the order to which we approximate the time evolution operator. So for example, we've used U tilde of tau above for the first order approximation. We usually write S1 of tau. And we write S1 of tau, what we mean is precisely what we had before. And in this scenario here, what we see is that the 1 here is just going to be telling us that we approximate to first order. Okay. So as a starting point, let's talk about the second order approximation. So for a Hamiltonian that's given like this, the sum of hj, and a small time step tau, we can write down a product formula that will approximate the time evolution operator to second order. Okay? And this is precisely the formula here. And we put 2 here because we're saying that this is second order approximation. And all this is just the same first order approximation formula being multiplied to another first order approximation formula that's reverse. So whereas here we went from j going from 1 to m with this product, once we get to the second product, we start from m and we go all the way back down to 1. Okay, so if you look at it just for two terms, what that looks like is it'll look like this. E to the A over 2, E to the B over 2, E to the B over 2, E to the A over 2. So that's all it is. And if you look at it for just two terms, A and B, that's what it's going to look like. But I've written it down here a bit more generally. The reason why I wrote it down generally and I didn't start, so I'm not going to show you the analysis for how to do these types of bounds to these product formulas, because they're very complicated and it's not so much different in terms of the logic of the proof that we just did. It's exactly the same thing. We just have a bit more complicated expansions to deal with. But if you want to bound on the precision, it's very, very straightforward. Follow the steps just as we did above, replacing u tilde with this product here, and repeating the analysis using your properties of inequality, the properties of norms, and you'll arrive at the following bound for the precision. Okay, and you can also find n using the same method that we did before. Find n such as exponential is approximately 1, and then you take the ceiling function. Okay, so what we also want to do is you also want to make a note that this approximation, and this is very important in closed quantum systems, is that this is a symmetric approximation, which means that under time reversal, the structure of this approximation is preserved. So if you go from t to minus t, you're not switching around the order or anything, it's preserved. So even if you look at the S2 of tau dagger, the order is going to be preserved, the order of the exponentials hj. And this symmetry becomes very important because this idea of symmetric approximation, or the symmetric approximation that I mentioned here, is what allowed Suzuki to recursively construct higher order product formulas using this as a starting point. So this, the proof that Suzuki wrote down to construct these higher order product formulas recursively, it's very complicated. And honestly, you can go through like a whole 2-3 lectures talking about this. But I'm just going to give you an idea of the logic of what he did. And what he did was he took the second order product formula, and for him, he didn't just use tau, but he used some, any scalar number, let's say lambda, and he took products of the second order product formula, and he kept taking products until such a time when the terms that he wanted in the Taylor expansions cancel. So like we did before, where we looked at the Taylor expansion of the time evolution operator and the Taylor expansion of our approximation, we looked at which terms cancel. So Suzuki spent a lot of time writing out Taylor series and taking products of the second order product formulas, and he kept writing Taylor series, and he manually checked which of these things cancel, and this allowed him to come up with a recursive formula, which he then proved inductively to construct higher order approximations. And as an example, Suzuki found that if you consider products of this form here, where this k is just any natural number, okay, then you can approximate the time evolution operator up to some order 2k. Now you may be wondering, okay, I'm saying 2k, that means I'm only approximating to even numbers. Well, if you so choose, you can, use the fourth order approximation to approximate third order formula. You just don't cancel the term. And that's why he doesn't do it for odd numbers, although you can write the recursive proof in that way. But in Suzuki's original paper, in fact, he was looking for a third order approximation for S2, and the third order for the unitary operator, and the third order approximation actually already had built in the terms for the fourth order approximation. So that's why we always use S to the power 2k. So in this case here, what you have is a very, very complicated formula that when you specify k, it will actually produce for you an approximation to your time evolution operator up to the order 2k. And as you can see here, this is built recursively, but if you start from like k is equal to say 2, then you have something like S2 squared on S2 times S2 squared with these arguments that are inside. Okay? Yeah, so that's just the shortest Suzuki product formula. And the analysis and the error bounds for this particular formula are very, very complicated. So we're not going to be talking about them in this talk. And I wouldn't even give it to you as homework to go back and try to do it. But there's just so much of literature on this topic, and you can find these bounds in that reference that I have on the slide with Suzuki's original paper. But I'll just state the bounds here so that you can see it very easily. Is that the difference between the time evolution operator and our Toyota-Suzuki 2kth order formula for some n to power n is going to be given by this bound here, where lambda is again the maximum of the norms of each of the individual terms in our Hamiltonian, and L is just going to be the number of terms in the Hamiltonian. Okay, and through some rigorous analysis, they also found that this n is going to be given by the ceiling function of the maximum of either of these two quantities here. So as I said, this is a very, very complicated proof, so I won't talk about it here. But another even more important quantity that we'll talk about in quantum computing, or when we implement this on a quantum computer, is the number of exponentials. Sorry about that. Is the number of exponentials that are found in this product formula. Okay, and basically what we found it to be is that we take n times the number of exponentials in an individual product of S2k minus 2, and it's precisely this term here. Okay, so we can now write down our first quantum simulation algorithm, and it's very straightforward. There's just a few steps. Okay, and it's that if we're given a Hamiltonian H for our system, we must write it in a form where it's a sum of Hj, such that each Hj can be exponentiated easily and has an efficient quantum circuit implementation. Okay. The next step is to pick some order k for the Toyota-Suzuki product formula you wish to use to approximate U of t. The third step is to compute all the necessary and relevant quantities, which is, for example, lambda. You specify a precision epsilon and a simulation time t, and you give some initial state psi of 0. And you use this to compute n. Okay? The step 4 would be to construct quantum circuits for each of these exponentials. And step 5 will be then to construct a gate set using this that will be implemented in a quantum computer where an initial state psi 0 that'll be the register for your initial state. And this is just, our first quantum simulation algorithm. There's many more that we'll talk about as we go along, but this is the most basic one. And as a quick example, we can talk about simulating the XX spin chain. Okay, what is this? This is just spins on a chain with only interaction terms. Okay, it's fairly straightforward Hamiltonian. And the reason why I choose this specific model is because the circuits for implementing the individual exponentials are very, very easy to construct because they're already in Nielsen and Schwann. So this is very, very straightforward. But the Hamiltonian here, we're just going to consider it for just 3 spins, because that's going to be very, very easy, okay? But this is not a nice form of the Hamiltonian. This is something that's like, it looks nice to write down because it gives you understanding if you're doing analysis, and you're trying to find things like the ground state, or you're doing some sort of quantum mechanics with it. But in quantum simulation, it's not in a decent enough form, because I can't find, if I just use it in the plain form, I still have to find the exponential of this plus this, which is still very, very complicated. So what I want to do is I'll choose these Hj's as just these individual terms here. And we have H1 to H4, which I've just written out explicitly. And in which case the sum here will go Hj from 1 to 4. That's just all we're going to do. So all I've done here is I've just written this sum out explicitly for m is equal to 3, and I've taken out each of the terms and made them my individual H's, because they're going to be easy to actually simulate. So what do you effectively want to simulate Well, you want to simulate some tensor product of 3 Pauli matrices. And Nielsen and Chuang already gives you a prescription on how to do that. Okay, so for example, if I want to simulate something like this, which is just Z tensor Z tensor Z, I can do it with just one extra ancilla qubit, right? And this is the circuit that does it. Very, very quickly, I can tell you, all this does is it checks the parity of the computational basis of the of your qubits, your 3 qubits in your system register, and it stores the parity in an ancilla, and it applies the phase e to the minus I delta t when the parity is even, and it applies the phase e to the I delta t when the phase is odd. Okay, so I just pull the circuit state out of Nielsen and Chuang. So using this circuit, we should be able, and we, of course, we uncompute the ancilla here. And this will apply a unitary that looks like this. Okay? So we have a circuit that already exists in Nielsen and Chuang. But what do we want to simulate? Well, we may want to simulate something like, x tensor I. So we need a way to sort of modify this Hamiltonian, but we can do that with single qubit gates because you have this relation here, which says that if you have u on e to the minus I h tau on your dagger, you can pull the u's into the top as a transformation of the Hamiltonian. So as an example, if I want to simulate something like z tensor x tensor z, all I'm going to do is I'm going to brace this e to the minus I z tensor z tensor z by Hadamard gates on the second qubit, and I get precisely what I want to simulate. Okay, so this is just a straightforward logic from Nielsen and Chuang. And what you can do as an exercise is to find the quantum circuits that correspond to each of these e to the minus I hj tau. And it's straightforward to do. It's the same logic that I just showed you. You start with that circuit from Nielsen and Chuang, and you transform it so that you're correctly simulating each of these hj terms from the Hamiltonian. I should mention as well, if you have something like an identity there, then you just don't check the parity of that qubit. But as I said, you can find this in Nielsen and Chuang. And once you do that, what you want to do is you want to choose an order for your Trotter-Suzuki formula. And in most practical cases, you're going to choose 2 and 4. Now, the reason why you choose 2 and 4 is, and we'll talk about this next week, is because the number of Trotter steps that you need, or the number of applications of your Trotter-Suzuki formula that you need, grow quite fast as you increase the order. So just as an example, if I specify a simulation time of 2 seconds, and I choose the most common procedure, the precision that you may use, which is just 10 to the minus 6. For our Hamiltonian, it's very easy. The maximum of the norms are always going to be 1, because each of the individual terms just have a norm of 1. And if we choose just the order k is 2, okay, just the second order approximation, the number of times you need to repeat that second order approximation formula is going to be 13,064. And if you want to count, the number of exponentials, sorry, this is supposed to be 4, but it'll be 4 times this number. So it's actually double what this number is. So it's something of the order of magnitude, 52,256. So that is a lot of gates that you're going to need to do to simulate this type of Hamiltonian. Just with 3 spins, it's a lot of gates. So what I should mention is that it makes Trotter-Suzuki product formulas very good for fault tolerant settings. However, for NITheCS settings, you're not going to have this many gates without running into some sort of just complete decoherence and information loss. But that's why, as a preview to next week, there are many newer quantum simulation techniques that rely on a lot more advanced tools such as qubitization and even things like oblivious amplitude amplification to reduce this number. Okay? There are even algorithms that rely on random compilation of your gate set, which can drastically reduce this number, however, at the cost of not being able to go above an order of approximation of 1. So it's always just a first order formula. So there are many, many ways to improve this, but the main idea I want to get across here, which is just the number of times you need to repeat this. It's 13,064 times. That's why we only do K's 2 and 4. Of course, K can be arbitrarily high, but as you keep increasing K, what you end up doing is you keep increasing this number. And I think the last estimate I did for a paper was these things range somewhere in the billions of terms. When you do a plot and you see, okay, on my y-axis, I need to actually do, 1, 2, 3, 4, 5, 6, 7, 8, and then I have 10 to the minus 9 at the top, because that's how many terms go into this type of expansion. Of course, there's no free lunch. So if we have, a good enough approximation and the analysis is quite easy, it means that, okay, there's a caveat somewhere. The caveat is in how many terms you will need in your Chota-Suzuki approximation, which then leads to how many gates you're going to need on your quantum computer. Okay, so I think that's where I want to end it for today. And next week, we will talk about more complicated quantum algorithms for simulating closed quantum systems. I won't go into details like I did today, but what I will mention is the key points and address the caveats. So we'll see algorithms that address the specific problem of, how many times you have to repeat your Trotter step. We will see algorithms that allow you to actually use something like, the amplitude amplification from Grover's algorithm to maybe just do a single step of an algorithm and still have high enough accuracy and precision instead of doing something like 13,000 steps. But yeah, so I think we'll end it there. Thank you for your time.
Hi, Ian. Thank you very much for another very nice lecture. Are there any questions for Ian at this stage? There was none in the Q&A, but maybe if participants want to raise their hand, we can give them the right to ask questions in person. Please, don't be shy.
There was a question in the Q&A, but I answered it, but I'm happy to ask this question to Ian so that we can give a more detailed answer.
Okay, sorry, you are faster than me. I missed that. Okay, please.
What's the best precision that one can obtain with the first order Suzuki Trotter formulas?
Okay, so the precision that we have, this is user specified. When you're using the algorithm, you're going to specify the precision. Remember, I mentioned earlier that, so let's go back to the first order Trotter-Suzuki slide. Let's look at it just for the most simplest case, okay, for just H1 plus H2. Okay, usually what you want to do is you choose the precision. Okay, so if you want to go as high as 10 to the minus 10 or 10 to the minus 12, okay, what does that mean? That means the precision gets smaller and smaller and smaller. But what does that mean for n? It's inversely related to the precision of the first order formula, which means that n is going to get larger and larger and larger. Of course, what's going to happen is that there's going to come a point where n is going to be so large that it's then unfeasible to use this formula. Which is also another reason why people looked at higher order Trotter-Suzuki formulas, is because as you get higher orders, and for a specific range of precision and simulation time, of course, n is not just 1 over epsilon, there's some other parameters at the top here, but you'll find a specific enough range where your chosen precision will give you an n that is, applicable or more practical to your simulation. So I think the most important thing to remember is that the precision you choose. You choose however high you want to simulate or to what precision you want to use the first order formula for. But whatever number n you get after that, that's going to also create problems in trying to implement that on a quantum device, which is why there's higher order formulas as well. But again, the caveat is the higher the order formulas you go, you may have to do it over short time scales. So there's also some other caveats. I don't know if that answers the question.
I think it did.
Yeah.
Thank you, Ian, for that. Any other questions? Please raise your hand or use the chat, the Q&A. Okay, that doesn't seem to be the case. Then, Ian, I guess that is a good sign that your lecture was very clear and to the point. And I'm sure, Ian, you will be happy to share the slides so that we can add them to the website next to the link to the YouTube video, so that people can go back and read it again. Yeah. So thank you very much again, Ian, and Ilya, also for the support, and thank you to all the participants. Thank you for filling out the little poll. That is very useful for us to know who takes part in these events, so that we can keep optimizing and improving what we offer. Yeah, and don't forget that in a week's time, same Zoom link, we will be here again for the third installment of this mini course. And in particular to the participants and to the more senior member of the participants, if you have suggestions for further mini schools, or if you want to volunteer one, please let us know. We are always looking for speakers and for interesting topic for this monthly event. So thank you very much again. Have a good afternoon, and please stay warm, as it is cold more or less all over the country. Thank you very much. Bye. All the best.